In the late evening hours of a clear night, you step outside your home and look up at the sky. But instead of the familiar scattered points of starlight against the darkness, your eyes are drawn to something far more spectacular. Stretching from one horizon to the other, a luminous arc cuts across the heavens like a brush stroke of light painted by the hand of some cosmic artist. It's brighter than the full moon, casting shadows on the ground below. This is not the sky you know. This is not the sky humanity has ever known. This is a sky dominated by rings. Rings like Saturn's, but circling Earth. For just a moment, allow yourself to imagine what that would be like. How different would our world be? How would the presence of this magnificent celestial feature have shaped not just our skies, but our cultures, our sciences, our very understanding of our place in the cosmos? The answer is that nearly everything would be different. From the moment the first human looked up in wonder, to the satellites that would struggle to pierce through the debris field, rings would have fundamentally altered the trajectory of human civilization. But before we can understand how rings would change our world, we need to understand how Earth would get rings in the first place. Let's rewind the clock. Way back. Perhaps 100 million years ago, or maybe just a few million. The exact timing depends on which formation scenario we're exploring, but the mechanism is always the same. It comes down to something called the Roche limit, named after the French astronomer Édouard Roche, who calculated it in the 1800s. The Roche limit is the minimum distance at which a celestial body can orbit a planet without being torn apart by tidal forces. Get too close, and gravity doesn't pull uniformly. The side facing the planet feels a stronger pull than the far side, and if the body is held together primarily by its own gravity rather than structural strength, it gets stretched and eventually ripped to pieces. For Earth, this limit sits at about 18,000 kilometers from the center of the planet, or roughly 12,000 kilometers above the surface. That's about 3 times higher than the International Space Station orbits today. Now, here's the key point. Any object that crosses this threshold and breaks apart doesn't just crash into Earth. Instead, the debris spreads out along the object's orbital path, forming a ring. This is exactly how we believe Saturn got its magnificent ring system, and it's how Earth would get one too. So, what could cause this? The most likely scenario is a collision. Imagine a small moon, perhaps 100 kilometers across, orbiting peacefully around Earth. Then, disaster strikes. Maybe it's hit by a large asteroid or comet. Maybe it collides with another moon. The impact doesn't have to destroy it completely. It just needs to knock it off course, sending it into a decaying spiral toward Earth. As this doomed moon crosses the Roche limit, tidal forces take over. The moon begins to stretch almost like taffy being pulled. Cracks form across its surface. Chunks break away. Within hours or days, the entire body disintegrates into billions of fragments ranging from tiny dust grains to boulders the size of houses. These fragments continue orbiting Earth, but now they're spread out in a vast disk. Over thousands of years, collisions between particles cause them to settle into a relatively thin plane, aligned with Earth's equator. Congratulations! Earth now has rings. But what would they actually look like? This is where things get truly spectacular. Saturn's rings, while breathtaking, are viewed from a distance that diminishes their impact. Even from Saturn's cloud tops, the rings would appear as a bright arc across the sky. But Earth is much smaller than Saturn. Our planet has a radius of about 6,400 kilometers compared to Saturn's 60,000. This means that rings at the same relative distance would appear much larger in our sky. Picture this. The main ring system extends from about 7,000 kilometers above Earth's surface, out to perhaps 80,000 kilometers. That's well within the orbit of the Moon, which sits at 384,000 kilometers. The inner edge of the rings would be clearly visible as a defined boundary, while the outer edge would gradually fade into darkness. From the equator, where you'd be directly beneath the ring plane, you'd see something remarkable. The rings would appear as a thin, bright line stretching from horizon to horizon, passing directly overhead. It would look like someone had drawn a luminous stripe across the sky with a ruler. This line would be brightest at the zenith, directly above you, and would gradually dim as it approached each horizon due to atmospheric haze and the increased thickness of atmosphere the light must pass through. But here's what makes it even more spectacular. This isn't just a static line. Because the rings are made of countless individual particles, each catching and reflecting sunlight, the line would shimmer and sparkle. You might see variations in brightness where the ring density changes. You might notice that some sections appear more blue, while others are tinged with red, depending on the composition and size of the particles in that region. Now, let's move away from the equator. Travel north or south to the mid-latitudes, say around 45 degrees, roughly the latitude of Portland or Minneapolis in the United States, or Bordeaux in France. Here, the perspective shifts dramatically. Instead of a line overhead, you'd see a massive arc rising from the southern horizon, sweeping upward across the sky, reaching its highest point toward the south, then descending back to the northern horizon. The arc would span roughly 150 degrees of sky. To put that in perspective, your outstretched hand at arm's length covers about 20 degrees. This arc would be more than 7 hand widths across. It would dominate the entire sky. The width of the arc would vary depending on how thick the rings are. If they're relatively thin like Saturn's main rings, which are only about 10 meters thick despite being hundreds of thousands of kilometers wide, the arc might appear to be just a few degrees wide. If the rings are thicker or more diffuse, the arc could span 10 or even 20 degrees, appearing as a broad band rather than a thin line. Continue traveling toward the poles, and the spectacle changes again. At 60 degrees latitude, the angle is even more extreme. The rings now appear to emerge from one horizon and sweep in a dramatic curve across the sky before plunging back down toward the opposite horizon. They no longer pass overhead, but remain confined to the southern half of the sky if you're in the northern hemisphere. The highest point of the arc is now only about 30 degrees above the southern horizon, but they're still brilliant, still magnificent, still utterly alien compared to anything in our current sky. Push even further north to 70 degrees, 80 degrees, approaching the pole itself. Here, the rings hug the horizon, appearing almost edge-on. At the pole, they would form a complete circle around the horizon, a glowing ring encircling your entire field of view at ground level. It would be like standing in the center of a vast stadium where the upper rim glows with ethereal light. And here's something our current night sky cannot offer. The rings would be visible during the day. Unlike stars, which are washed out by sunlight scattering in our atmosphere, the rings would be bright enough and large enough to remain visible even in full daylight. They would appear as a pale white or silver band against the blue sky, similar to how the moon is visible during the day. In the moments around sunrise and sunset, when the sky takes on those dramatic oranges and reds, the rings would glow with borrowed color, turning rose and gold and crimson. Photographers would build entire careers around capturing the rings at different times of day, in different weather conditions, from different locations. The aesthetic of our world would be fundamentally different. But the rings don't just sit there unchanging. They would go through phases, much like the moon. During the day, when the sun is high in the sky, the rings would be fully illuminated on the side facing Earth. They would appear at their brightest, reflecting sunlight down onto the planet's surface. At night, when Earth is between the sun and the rings would be in Earth's shadow. They would disappear almost entirely, visible only as a dark band blocking out the stars behind them. This creates an interesting phenomenon. For a few hours each night, the stars in the area of sky where the rings are located would simply vanish. Ancient astronomers would have called this the dark river, or the void, or the path of shadows. They would have woven elaborate mythologies about what dwells in that darkness, what it means when certain stars disappear behind it, what omens could be read from its edges. The transition between day and night would offer spectacular displays. As the sun sets, the angle of illumination changes. The rings would remain brightly lit even after the sun has dropped below your horizon, because they extend so high above Earth's surface. You'd see a glowing arc shining in the darkening sky, a bridge of light connecting the sunset on one horizon to the opposite horizon where the sky is already dark. This would last for an hour or more after sunset, depending on your latitude and the season. The rings would gradually dim as Earth's shadow creeps across them from east to west. You'd literally watch the darkness consume the rings piece by piece, like a curtain being slowly drawn across a illuminated stage. The reverse would happen at dawn. Before the sun rises, while the sky is still dark, the western edge of the rings would suddenly flare to life as sunlight strikes them. The glowing arc would brighten and expand eastward, announcing the coming dawn long before the sun itself appears on the horizon. And then there are the eclipses. Oh, the eclipses. Not just eclipses of the sun by the moon, which would still happen, but eclipses of the sun by the rings. Because the rings lie in Earth's equatorial plane, and because Earth's axis is tilted 23.5 degrees relative to its orbit around the sun, the rings would cast a shadow on Earth's surface for much of the year. Picture a massive shadow band, hundreds of kilometers wide, sweeping across the equatorial regions. This shadow would move as Earth rotates, creating a zone of permanent twilight that migrates around the planet. If you lived within about 30 degrees of the equator, you'd experience this ring shadow for several hours each day during certain seasons. The temperature would drop noticeably. The light would take on a strange, diffused quality, because you're not in complete darkness. Light scattered by the atmosphere still reaches you, and some light filters through the thinner parts of the rings. It would be like living under a perpetual partial solar eclipse for a few hours every single day. The intensity and duration of these ring shadows would vary with the seasons. Earth's axial tilt means that during the June solstice, the northern hemisphere is tilted toward the sun, and the rings would cast their shadow primarily on the southern hemisphere. During the December solstice, the reverse would be true. But twice a year, during the equinoxes in March and September, something extraordinary would happen. For a few days, the sun would align perfectly with Earth's equatorial plane, which means it would align perfectly with the ring plane. When this happens, the rings would appear edge-on when viewed from the sun's perspective. Their shadow on Earth would shrink to almost nothing, just a thin line. but more dramatically. When you looked up at the rings from Earth's surface, they would seem to vanish. Because they're so thin, when viewed exactly edge-on, they'd be nearly invisible. For a few days, twice a year, the rings would disappear from the sky entirely. Ancient civilizations would have marked these days with major festivals. The vanishing, the days of darkness, the time when the bridge closes. The return of the rings a few days later would be celebrated as a rebirth, a renewal, proof that the cosmic order continues. Now, let's talk about what the rings are made of. This matters because it affects their appearance. If Earth's rings formed from a moon that was mostly ice, like many of the moons in the outer solar system, the rings would be extremely bright and white, reflecting up to 90% of the sunlight that hits them. They'd be absolutely dazzling, potentially bright enough to read by at night when they're fully illuminated. If the rings formed from a rocky moon or asteroid, they'd be darker, reflecting only 10 to 30% of sunlight. They'd still be visible and impressive, but they'd appear gray or brown rather than brilliant white. There might also be variations within the rings themselves. Different regions might have different compositions. You might have a bright, icy ring interspersed with darker, rocky bands. Some sections might be dense and opaque, while others are so diffuse they're barely visible. Gaps might form, similar to Saturn's Cassini division, where the gravitational influence of small shepherd moons has cleared out a region of the rings. These gaps would appear as dark bands cutting through the bright arcs, adding structure and complexity to the display. The rings would also have a granular structure if you looked closely enough. They're not a solid surface, but countless individual particles. From Earth's surface with the naked eye, they'd appear smooth and continuous. But through a telescope, even a small one, you'd start to see texture. Clumps and streamers where particles have temporarily gathered. Waves and ripples where gravitational resonances create patterns. Transient bright spots where a collision between larger chunks has created a fresh cloud of reflective debris. Observing the rings would be a hobby in itself. Amateur astronomers would catalog features, track changes, compete to photograph the finest details. And there's one more aspect we need to consider: the scale of illumination. The rings would be huge and reflective. Even if they only reflected a fraction of the sunlight hitting them, the total amount of light they send back toward Earth would be significant. Some estimates suggest that on a clear night with the rings fully illuminated, they could provide as much light as several full moons. This would fundamentally change the nature of night on Earth. True darkness would be rare, occurring only when the rings are in shadow and the moon is also absent. For most of human history, nights would be much brighter. You'd be able to walk outside without a torch or lantern and see quite clearly. Nocturnal animals would face different selective pressures. Plants that rely on photoperiod for flowering might bloom at different times. The entire ecology of night would be transformed. But perhaps the most profound change would be psychological and cultural. Humans have looked up at the sky for hundreds of thousands of years, finding patterns in the stars, navigating by celestial markers, wondering what lies beyond. In our timeline, the sky is vast and mostly empty, punctuated by tiny points of light. It's easy to forget we're on a planet. It's easy to think of Earth as the ground beneath our feet and everything else as distant and separate. But with rings, that illusion would be impossible to maintain. Every single day and night, you'd see undeniable proof that Earth is a world in space, a sphere with something orbiting around it. The rings would be a constant reminder of cosmic mechanics, of gravity, of the fact that we live on a planet among planets. This would shape mythology, religion, philosophy, science. Ancient peoples would develop sophisticated models of the cosmos much earlier, driven by the need to explain this dominant feature of their sky. The rings would be in every creation myth, every religious text, every artistic tradition. They would be as fundamental to human culture as the sun and moon. More so, because they're always there, always visible, always changing yet always constant. They would be woven into the very fabric of what it means to be human on this altered earth. This is the world we're about to explore. A world where rings are not some distant feature of other planets, viewed through telescopes and spacecraft cameras, but an intimate part of daily life. Where every human who has ever lived grew up seeing that arc across the sky and wondering what it meant. Where the ground beneath your feet and the light show above are forever connected by gravity and motion and the strange beauty of cosmic accident. Welcome to Earth, the planet with rings. The first humans to ever look up at a ringed sky had no telescopes, no physics, no understanding of orbital mechanics. What they had was wonder and fear, and an overwhelming need to explain the impossible thing hanging above them. Imagine being an early human, maybe 50,000 years ago, standing on an African plain or huddled in a cave in Europe. You look up and see a glowing bridge stretching across the entire sky, brighter than anything except the sun and moon. It moves with perfect regularity. It changes with the seasons. It casts shadows that sweep across the land. What would you think? What stories would you tell? In our timeline, humans developed hundreds of different creation myths, each shaped by local geography, climate, and culture. But in a world with rings, certain themes would appear everywhere, in every culture, on every continent. The rings would be too prominent, too universal to interpret in wildly different ways. They would be the central feature of every cosmology. Most likely, the rings would be seen as a bridge, the bridge between worlds, the path of the gods, the road to the heavens. This interpretation makes intuitive sense. The rings connect one horizon to the other. They're clearly not part of the Earth itself, because they're up in the sky, but they're also clearly connected to Earth in some way, because they don't move like the sun or moon or stars. They stay in one place relative to the ground. They must be a structure, a pathway, a connection between the realm of mortals and the realm of the divine. In countless mythologies, you'd find stories of heroes or shamans who journey along the rings to meet the gods. You'd have tales of souls traveling the bridge after death, walking from one end of the world to the other, ascending into paradise or descending into punishment. The rings would be a literal stairway to heaven, visible to everyone, taunting humanity with a destination we cannot reach. But the rings aren't static. They go through daily and seasonal changes. This would add layers to the mythology. When the rings are bright and fully illuminated, the bridge is open. The gods are watching. This is a time for rituals and prayers. When the rings are in shadow, dark and invisible, the bridge is closed. The gods have turned away. This is a time of danger, when evil spirits might cross over, when the natural order is disrupted. Cultures living near the equator, who experience the ring shadow every day, would build their entire religious calendar around it. The hours of shadow would be sacred time, or forbidden time, or time for specific ceremonies designed to protect the community while the bridge is dark. The equinoxes, when the rings appear edge-on and nearly vanish for a few days, would be the most important days of the year. Every culture would mark this time with major festivals: the dyeing of the bridge, the closing of the way, the time of testing. For those few days, the connection between Earth and the heavens is severed. Anything could happen. The sun might not rise, the seasons might not change, the crops might fail. Priests would perform elaborate rituals to ensure the ring's return. Sacrifices would be made. Communities would fast or feast. And when the rings reappeared, growing thicker and brighter each day, there would be celebration unlike anything else in the calendar. The bridge has returned. The gods are with us again. The world is renewed. This would be the new year, the moment when time resets and the cycle begins again. Now, let's talk about navigation. In our world, early sailors and travelers relied on the stars. The North Star, Polaris, is famous for remaining almost stationary in the northern sky, allowing anyone in the northern hemisphere to determine which direction is north. The stars rise and set in predictable patterns. The sun and moon follow paths across the sky that change with the seasons. These celestial markers made long-distance navigation possible, but it required knowledge and practice. You had to learn which stars were which. You had to understand how their positions changed throughout the night and year. In a ringed world, navigation would be vastly simpler. The rings are always there. They're aligned with Earth's equator. If you can see the rings, you can orient yourself instantly. Say you're a sailor in the Mediterranean, roughly 35 degrees north latitude. You look up and see the ring arc stretching across the sky. The highest point of that arc is always due south. Always. It doesn't matter what time of day or night it is. It doesn't matter what season it is. The rings are your compass, accurate to within a degree or two, visible in any weather clear enough to see the sky. This means seafaring cultures would develop earlier and travel farther. The Phoenicians, the Polynesians, the Vikings, all the great seafaring peoples of our history. They would have been even more accomplished with rings to guide them. Trade networks would span greater distances. Colonies would be established in more remote locations. The age of exploration might come 1,000 years earlier, because navigation is so much easier when you have a permanent reference line painted across the sky. Land navigation would be equally transformed. Caravans crossing the Sahara or the steppes of Asia would never get lost. You always know which direction you're heading relative to the rings. Ancient roads would be built in alignment with them. North-south roads would parallel the highest point of the ring arc. East-west roads would cut perpendicular to it. Cities would be laid out with the rings in mind. Major streets would align with ring shadow patterns. Temples and palaces would be positioned so that on certain days the ring shadow would fall across the entrance at precisely the moment of some significant ceremony. And, speaking of alignment, we need to talk about ancient astronomy. In our world, early astronomers tracked the motions of the sun, moon, planets, and stars. They noticed patterns. They made predictions. Eventually, after thousands of years of observation, people like Copernicus and Kepler figured out that Earth and the other planets orbit the sun, that the moon orbits Earth, that gravity governs these motions according to mathematical laws. This process took a very long time because the evidence is subtle. The stars are so distant that their parallax is imperceptible without telescopes. The planets move in complex patterns that can be explained by either geocentric or heliocentric models. There was room for debate, for different interpretations. But with rings, everything changes. the rings orbit Earth. This is obvious. They don't move with the stars. They don't rise and set like the sun. They're fixed relative to the ground, which means they must be orbiting around Earth. Any ancient astronomer who paid attention would realize this within a few years of observation. And once you understand that the rings orbit Earth, it becomes much easier to understand that the Moon also orbits Earth. The Moon passes in front of the rings sometimes. It occults them. This would be a spectacular sight, by the way. The Moon moving slowly against the backdrop of the bright rings, gradually covering them. The dark disk of the Moon would be outlined by the brilliant light of the rings behind it. These occultations would happen regularly, and they would demonstrate that the Moon is closer to Earth than the rings are, because it can pass between us and them. With this knowledge, ancient astronomers would start measuring. How far away are the rings? How fast do they move? They'd notice that the inner parts of the rings move faster than the outer parts. This is a direct observation of Kepler's laws of planetary motion. The same laws that govern planets orbiting the Sun also govern ring particles orbiting Earth. A clever astronomer in ancient Greece or China or India might figure this out 1,000 years before Kepler was born in our timeline. They might calculate the mass of Earth based on the orbital period of the rings. They might predict where the rings will be at any given time with extraordinary accuracy. The scientific revolution could come much, much earlier. But there's a flip side. The rings might also delay scientific progress. If every culture's religion is built around the rings as a bridge to the divine, questioning that interpretation becomes heresy. Suggesting that the rings are just rocks and ice orbiting due to natural forces, that there's nothing sacred about them, that they're no different from a moon or a planet, this might get you killed. In our timeline, Galileo was persecuted for suggesting Earth orbits the Sun. In a ringed timeline, someone suggesting the rings are natural rather than divine might face similar or worse persecution. So it's possible that scientific understanding of the rings comes very early, in some enlightened culture that values observation over dogma. Or it's possible that the religious significance of the rings suppresses scientific inquiry for centuries. Either way, the rings would be the dominant force shaping astronomical thought. Let's move on to calendars and timekeeping. In our world, most ancient calendars were based on the moon, because lunar phases are easy to observe and count. Some cultures used solar calendars based on the equinoxes and solstices. The challenge was that lunar months and solar years don't sync up neatly, so you get complex systems with intercalary months and leap years. In a ringed world, you have an additional timekeeping tool, the ring shadow. For cultures near the equator, the ring shadow sweeps across the land every single day. You can tell time by its position. Early morning, the shadow is in one location. Noon, it's moved to another. Evening, it's somewhere else. This gives you a natural clock, visible to everyone, that doesn't require any technology. Sundials would still be invented, of course, but they'd be secondary to the ring shadow. In fact, the ring shadow would be the primary way most people told time until mechanical clocks were invented. The seasonal changes in the rings would also provide calendar markers. As Earth's axial tilt causes the ring shadow to shift north and south throughout the year, you can track the seasons by observing where the shadow falls. Ancient farmers would plant crops when the shadow reaches a certain latitude. They'd harvest when it reaches another. This would be more reliable than counting days, because it's based on direct observation of a celestial phenomenon. You can't lose track of it. You can't make an error. The rings themselves tell you what time of year it is. This means agriculture would be more precise. Crop yields would be higher. Famines caused by planting at the wrong time would be less common. Civilization might develop faster and more stably as a result. Now, let's imagine the monuments. In our world, ancient peoples built structures aligned with astronomical phenomena. Stonehenge is aligned with the summer solstice sunrise. The pyramids of Giza are aligned with cardinal directions and certain stars. The Mayan pyramids have features that mark equinoxes. These monuments took enormous effort to build, and they served both practical and religious purposes. They were calendars, temples, and demonstrations of cosmic knowledge. In a ringed world, the monuments would be even more spectacular. Imagine a stone circle like Stonehenge, but designed so that on the equinox, when the rings appear edge-on, they align perfectly with a sight line through the stones. On that day, and only that day, the rings would seem to pass through the monument, connecting earth and sky. Or imagine a massive temple built at the equator, with a long corridor that runs perfectly east-west. Twice a year, during the equinoxes, the ring shadow would sweep through this corridor at a precise time, plunging it into darkness. This would be the moment for the most sacred ritual of the year. Priests would stand in the corridor as the shadow approaches, visible as a band of darkness racing across the landscape. The shadow would engulf them. For a few minutes, they'd stand in twilight while the world outside remains bright. Then the shadow would pass, and light would return. The gods have accepted the offering. The cycle continues. Or consider a pyramid, its sides aligned with the ring plane. At certain times of year, the ring shadow would fall across one face but not the others, creating a stark contrast of light and shadow that would creep across the structure as the day progresses. Thousands of people would gather to watch this spectacle, interpreting the exact timing and appearance as omens. Did the shadow cover the face completely? Did it leave a sliver of light at the edge? Does this predict a good harvest or a hard winter? Priest astronomers would spend their entire lives studying these patterns, making predictions, advising kings and emperors. Art and culture would be utterly saturated with ring imagery. In our world, the sun and moon appear in art from every culture. They're universal symbols. In a ringed world, the rings would be even more prevalent. Every ancient pottery shard, every cave painting, every carved relief would feature the rings. They'd be stylized in different ways. Some cultures might represent them as a simple arc or line. Others might depict them as a bridge with elaborate details. Still, others might show them as a living entity, a serpent or dragon encircling the world. But they'd always be there. You couldn't create art without including them. They'd be the visual motif that defines human creativity. Music and poetry would reference the rings constantly. Epic poems would describe heroes journeying along the ring bridge. Love songs would compare a beloved's beauty to the brightness of the rings at sunset. Dirges would speak of souls walking the darkened bridge to the afterlife. The rings would give poets a shared vocabulary, a set of images and metaphors that everyone would understand regardless of language or culture. This would make cultural exchange easier in some ways. A Greek poet and a Chinese poet might not speak the same language, but they'd both understand what it means to say, bright as the ring at zenith, or dark as the shadow band. And what about written language? It's possible that some writing systems would incorporate ring-related symbols. Maybe a curved line represents the rings and becomes a word for sky, or divine, or eternal. Maybe the shape of certain letters is inspired by the ring arc, as seen from different latitudes. The Phoenician alphabet, which evolved into Greek and Latin and eventually most modern alphabets, might look completely different if the scribes who created it were inspired by the rings rather than other sources. Now, let's talk about the darker side of all this. Rings would influence warfare and conflict. Imagine two armies meeting on a battlefield near the equator. One general positions his forces so that during the battle, the ring shadow will sweep across the enemy position. For a crucial hour, the enemy would be fighting in twilight while his own forces remain in bright sunlight. This is a real tactical advantage. Visibility would be reduced for the enemy. Their morale might falter because fighting in the shadow could be seen as a bad omen. Some cultures might have religious prohibitions against fighting in the ring shadow, believing it angers the gods. A clever commander could exploit this. Alternatively, some warrior cultures might embrace the shadow. Berserkers or fanatics who fight in the ring shadow, using the reduced visibility to launch surprise attacks, terrifying enemies who believe they're being attacked by shadow demons. Entire military doctrines would develop around ring shadow tactics. Fortifications would be built with the rings in mind. Castles and city walls would have sight lines that align with the ring arc, allowing defenders to use the rings as a reference for aiming artillery or archers. Watchtowers would be positioned at locations where the rings are most visible, because clear visibility of the rings means clear weather and good conditions for spotting approaching enemies. The rings would be integrated into every aspect of military planning and strategy. And what about the psychological impact on individuals? Growing up under a ringed sky would shape how people think about the cosmos and their place in it. Children would ask their parents what the rings are. They'd be told stories, religious explanations, or scientific facts, depending on the time period and culture. But everyone would grow up knowing that the sky is not empty, that Earth is not alone, that there's something else out there, orbiting us, connected to us, part of our world yet separate from it. This might make people more or less religious depending on how you look at it. On one hand, the rings could be seen as proof of divine design. Something so beautiful and perfectly regular must be the work of gods. On the other hand, the rings could inspire scientific curiosity. What are they made of? How do they stay up there? Why do they move the way they do? Both impulses would exist in every culture, sometimes in conflict, sometimes in harmony. There's also the question of whether people would feel more connected to the cosmos or more isolated. In our world, we look up and see stars, impossibly distant, and we wonder if anyone else is out there looking back. In a ringed world, you look up and see something that's part of your world. The rings orbit Earth. They're ours. This might make the universe feel more comprehensible, more within reach. Or it might make Earth feel more special, more set apart. Why does Earth have rings when the sun and moon don't? Are we the center of creation? Are the rings a gift or a prison? These questions would haunt philosophers for millennia. And finally, consider how the rings would affect our sense of beauty. In our timeline, a truly dark night sky filled with stars is considered one of the most beautiful natural sights. People travel to remote locations to escape light pollution and see the Milky Way arching overhead. But in a ringed timeline, the Milky Way would always be partially obscured by the rings. On the other hand, you'd have the rings themselves, which would be far more dramatic than anything in our current sky. Beauty is subjective, shaped by familiarity. People in a ringed world wouldn't miss the unobstructed star field because they'd never known it. They'd find beauty in the way the rings catch the first light of dawn, in the sparkle of individual ring particles on a clear night, in the rare moments during the equinox when the rings vanish and the stars shine through unimpeded. That moment, that brief window when the sky looks the way we see it now, would be considered the most beautiful time of the year. Poets would write about it. Artists would try to capture it. And when the rings returned, people would feel relief and joy, welcoming back the familiar feature that makes their sky home. We've talked about what the rings would look like and how they'd shape human culture, but now it's time to dig into the physics. Because rings aren't just beautiful. They're complex, dynamic, and sometimes terrifying systems governed by gravity, orbital mechanics, and the endless dance of billions of particles colliding in space. Understanding the science behind Earth's rings means understanding why they exist, how they stay stable, and what consequences they'd have for the planet below. Let's start with the fundamental question. Why would the rings stay in orbit instead of falling down or flying away into space? The answer lies in orbital mechanics, the same principles that keep the moon circling Earth and Earth circling the sun. Any object in orbit is actually falling toward the planet it orbits, but it's also moving sideways fast enough that it keeps missing. Imagine throwing a ball horizontally. It follows a curved path and hits the ground some distance away. Now throw it faster. It travels farther before hitting the ground. Throw it fast enough, and the curve of its path matches the curve of Earth's surface. It never hits the ground. It's in orbit. For an object just above Earth's atmosphere, this requires a speed of about 7.8 kilometers per second. The ring particles are much higher up, so they orbit more slowly, but the principle is the same. Each particle is constantly falling toward Earth, but also constantly missing, tracing an elliptical or circular path around the planet. Now, here's where it gets interesting. The rings aren't a solid object. They're made of countless individual pieces, each in its own orbit. And these pieces are constantly colliding with each other. When two ring particles collide, they exchange momentum. If one is moving faster and the other slower, the collision tends to average out their speeds. Over thousands and millions of collisions, this process causes all the particles in a particular region of the rings to orbit at roughly the same speed. It also causes the rings to flatten into a thin disk. Any particle with an orbit tilted relative to the main ring plane will collide with other particles. These collisions gradually change its orbit until it's moving in the same plane as everything else. This is why Saturn's main rings are only about 10 meters thick despite being hundreds of thousands of kilometers wide. The same process would happen with Earth's rings, creating a disk so thin it would appear almost two-dimensional from certain angles. But the rings wouldn't be uniform. Different regions would have different densities, different particle sizes, and different optical properties. Near the inner edge, where particles orbit fastest, the ring might be relatively sparse. Particles here are moving at tremendous speed, several kilometers per second, and collisions are frequent and violent. Many particles would be shattered into smaller pieces or knocked into trajectories that send them spiraling down into Earth's atmosphere. The result is a region that's constantly losing material, but also constantly being replenished by particles migrating inward from farther out. In the middle regions, you'd have the densest, most stable part of the ring system. Particles here orbit at a more moderate pace, collisions are less destructive, and the system reaches a kind of equilibrium. This is where the rings would appear brightest and most solid from the ground. Toward the outer edge, the rings would become more diffuse again. Particles orbit slowly, spread out over a larger area. The outer boundary of the rings might be poorly defined, gradually fading into scattered debris that's barely visible. And then there are the gaps. Just like Saturn's rings have divisions like the Cassini division and Encke gap, Earth's rings would develop similar features. These gaps are created by orbital resonances with moons or larger chunks of debris within or near the ring system. Here's how it works. Imagine a small moon orbiting just outside the main ring system. Every time a ring particle completes, say 3 orbits, the moon completes exactly 2. This means the particle and moon repeatedly pass near each other at the same point in their orbits. Each time they pass, the moon's gravity gives the particle a slight tug. Over many orbits, these repeated tugs add up, gradually changing the particle's trajectory until it's either pushed inward or outward, clearing a gap. The moon is called a shepherd moon because it herds the ring particles, maintaining the sharp edges of the gap. Earth's rings would likely have several such shepherd moons, small bodies that survived the collision that created the rings or were captured afterward. These moons would be visible from Earth, tiny points of light moving against the backdrop of the rings, their positions shifting night by night. Ancient astronomers would track them obsessively, noting their periods, predicting their positions, possibly even naming them after gods or heroes. Now let's talk about what happens when ring particles collide. Most collisions are gentle, just particles brushing against each other, exchanging momentum, maybe chipping off small fragments. But occasionally you would get a much more energetic collision. 2 large chunks, maybe boulders several meters across, slamming into each other at kilometers per second. The impact would shatter both objects, creating a cloud of smaller fragments. From Earth, this might appear as a sudden bright spot in the rings, a transient flare of reflected sunlight from all the fresh, highly reflective debris. Over the following days and weeks, this debris cloud would spread out along the orbit, eventually merging back into the general ring population. Amateur astronomers would watch for these events, reporting them to scientific organizations, debating whether they're increasing in frequency or following some pattern. But here's a critical point that we haven't addressed yet. The rings are not permanent. They're slowly decaying. There are several processes that cause this. First, there's atmospheric drag. Earth's atmosphere doesn't have a sharp cutoff. It gradually thins with altitude, but even at the altitude of the rings, there are still a few stray atoms of oxygen and nitrogen. Ring particles moving through this tenuous atmosphere experience drag, just like a spacecraft in low Earth orbit. It's incredibly slight, but over millions of years it adds up. Particles gradually slow down, their orbits decay, and they spiral inward toward Earth. Eventually, they hit the denser parts of the atmosphere and burn up like meteors. The second process is called Poynting-Robertson drag. Sunlight carries momentum. When photons from the sun hit a ring particle, they give it a tiny push. Because the particle is orbiting Earth, it's moving through the sunlight at an angle, and the net effect is that the particle loses orbital energy and spirals inward. This effect is strongest for small particles, dust-sized grains that have a lot of surface area relative to their mass. Over time, the rings would lose their smallest particles preferentially, causing the average particle size to increase. Third, there's the interaction with Earth's magnetic field. Charged particles from the solar wind and Earth's radiation belts can collide with ring particles, sputtering atoms off their surfaces. If a ring particle is made of ice, these collisions can knock water molecules loose. The water molecules are then swept away by Earth's magnetic field or broken apart by solar ultraviolet light. This process gradually erodes the rings from the inside. All of these processes combined mean that Earth's rings would have a finite lifetime. Estimates vary depending on the initial mass and composition of the rings, but a reasonable guess is anywhere from 10 million to 100 million years. That sounds like a long time, and it is, but it's nothing compared to Earth's age of 4.6 billion years. If Earth had rings today, they would have formed relatively recently in geological terms. Perhaps they're the remnants of a moon that was destroyed by an asteroid impact during the late heavy bombardment 4 billion years ago, and we're seeing the tail end of the ring system's lifespan. Or perhaps they formed much more recently, maybe only a few million years ago, and they'll persist for tens of millions of years into the future. Either way, the rings are temporary. They won't last forever. This adds a poignant element to the whole scenario. Humans living under ringed skies would take them for granted, assuming they've always been there and always will be. But a scientifically advanced civilization would eventually realize the truth. The rings are dying. Slowly, imperceptibly, but inevitably, they're falling apart. The beautiful arc that has dominated the sky for all of recorded history will one day fade and vanish. Now, let's turn to one of the most dramatic consequences of having rings, the meteor problem. Ring particles don't just stay in orbit forever. As we've discussed, they gradually spiral inward, and when they hit the atmosphere, they burn up. From the ground, this looks like a meteor, a shooting star, a brief streak of light across the sky. In our world, meteors are relatively rare. On a clear, dark night away from city lights, you might see a few per hour during normal conditions or dozens per hour during a meteor shower. But in a world with rings, meteors would be constant. Every single night, all night long, you'd see shooting stars. Dozens per hour. Hundreds per hour in some locations. The sky would be alive with streaks of light, a never-ending celestial fireworks display. This would be normal. Children would grow up thinking this is just what the night sky looks like. The phrase, "make a wish on a shooting star," would be meaningless, because shooting stars wouldn't be rare or special. But here's the problem. Not all ring particles burn up completely. The smaller ones, yes. Anything smaller than a pebble would vaporize in the upper atmosphere, creating the harmless light show. But larger chunks, anything from the size of a fist to the size of a car, would make it through. These meteorites would rain down on Earth constantly. Most would fall in the oceans or uninhabited areas, but some would hit populated regions. Buildings would be damaged. People would be killed. Every culture would have stories of death from above, rocks falling from the ring bridge, divine punishment, or cosmic bad luck. Architecture would adapt. In regions where meteorite strikes are most common, particularly near the equator where the ring density is highest directly overhead, buildings would have reinforced roofs. Maybe thick stone vaults designed to withstand impacts. Or maybe buildings would be built partially underground, with only small openings to the surface. Public spaces might have covered walkways connecting structures, so people don't have to expose themselves to the sky. There might be a cultural taboo against looking up, because the moment you look up is the moment a rock might hit you. And it's not just the direct impacts. When a large meteorite hits the ground, it creates a shock wave. If it lands in a city, the explosion could level multiple buildings. If it lands in the ocean near a coast, it could create a tsunami. Coastal civilizations would be constantly at risk. They'd develop early warning systems, watchtowers scanning the sky for incoming fireballs, signal fires or bells to alert people to seek shelter. Maritime trade would be more dangerous because ships at sea have no protection from meteorite strikes. Sailors would pray to the gods of the rings for safe passage. Insurance, if such a concept existed, would be astronomically expensive for ocean voyages. Some cultures might avoid seafaring altogether, staying inland where at least you have a roof over your head. Over millions of years, this constant bombardment would have another effect: erosion. The equatorial regions would be pockmarked with impact craters, small ones mostly, but cumulatively they'd wear down the landscape. Any structures built in these regions would degrade faster than in our timeline. Ancient ruins would be more ruined. The pyramids of Egypt, if they existed in this timeline, might be significantly more damaged, their smooth limestone casing stones chipped and cracked by countless small impacts. On the other hand, this might spur technological development. Cultures that figure out how to predict where meteorites will fall or build better protective structures would have an advantage. The need to cope with ring fall might drive innovation in materials science, architecture, and early warning systems. Now, let's talk about tides. In our world, tides are caused primarily by the moon's gravity, with a smaller contribution from the sun. The moon pulls on the side of Earth, facing it more strongly than it pulls on Earth's center, and it pulls on Earth's center more strongly than it pulls on the far side. This differential force creates a bulge in Earth's oceans on both the near and far sides, and as Earth rotates through these bulges, we experience high and low tides. The rings would add another layer of complexity. Each ring particle has gravity, and while an individual particle's gravitational pull is negligible, the combined mass of trillions of particles adds up. The total mass of the rings would probably be less than the moon's mass by several orders of magnitude, so their tidal effect would be much weaker. But it wouldn't be zero. The rings are spread out in a disk around Earth's equator, which means their gravitational pull is distributed differently than the moon's. The strongest pull would be directly above and below the equator, creating a slight compression of Earth along the equatorial plane. This would cause a very subtle change in tidal patterns. Equatorial coasts might experience slightly higher high tides and slightly lower low tides. The effect would be small, probably less than a few centimeters, but over time, it would influence coastal erosion patterns and sedimentation. Ancient coastal settlements might be built in slightly different locations to account for these modified tidal ranges. More significantly, the rings would affect Earth's rotation over very long timescales. Just as the moon's tidal forces are gradually slowing Earth's rotation and causing the moon to drift farther away, the rings would exert their own tidal drag. However, because the rings orbit much closer than the moon, and in Earth's equatorial plane, the dynamics are different. The rings would tend to synchronize with Earth's rotation. If the rings orbit faster than Earth rotates, they'd pull Earth along, speeding up the rotation slightly. If they orbit slower, they'd act as a brake. Given the likely orbital distances for Earth's rings, they'd probably orbit faster than Earth rotates, which means they'd actually counteract the moon's slowing effect to a small degree. Earth's day would be slightly longer than it would be without rings, but not by much. maybe a few seconds over millions of years. Not enough for anyone to notice without precise timekeeping. But there's another, more interesting effect. Axial precession. Earth's axis wobbles like a spinning top, a phenomenon called precession. It takes about 26,000 years for the axis to complete one full wobble. This wobble is caused by the gravitational pull of the Sun and Moon on Earth's equatorial bulge. The rings, being concentrated in the equatorial plane, would add mass to that bulge. This would increase the rate of precession. Instead of 26,000 years, it might complete in, say, 22,000 years. This doesn't sound like a huge difference, but precession affects which stars are considered pole stars, and where the Sun appears in the sky relative to the background stars during equinoxes and solstices. Ancient astronomers who track these changes over centuries would notice that the cycle completes faster. They might interpret this as evidence that time itself is speeding up, that the cosmic order is accelerating toward some prophesied endpoint. Entire religious movements might spring up around this observation. There's also the question of Earth's axial stability. In our timeline, the Moon acts as a stabilizer, keeping Earth's axial tilt relatively constant at 23.5 degrees. Without the Moon, Earth's axis would wobble chaotically over millions of years, sometimes tilting more than 45 degrees, causing extreme seasonal variations that would make complex life difficult. The rings, being in the equatorial plane, would provide some additional stabilization, but much less than the Moon. The net effect depends on the total mass of the rings. If they're relatively light, their stabilizing influence would be minor. Earth would still rely primarily on the Moon for axial stability. But if the rings are very massive, perhaps comparable to a small moon, they could contribute noticeably to keeping the axis stable. This would be especially important if the collision that created the rings also disrupted or destroyed one of Earth's pre-existing moons. In that scenario, the rings might partially compensate for the lost stabilizing influence. Finally, let's discuss the long-term fate of the rings. We've established that they're decaying, slowly spiraling inward and raining down on Earth. But what does the endgame look like? Over tens of millions of years, the rings gradually thin out. They become less opaque, less bright. The brilliant arc that once dominated the sky starts to fade. By this point, human civilization, if it still exists, has probably figured out what's happening. Scientists have calculated the rate of decay. They know the rings have, say, 10 million years left. What do people do with this knowledge? Do they mourn the impending loss of the feature that has defined human existence since the beginning? Do they see it as a cosmic tragedy, the slow death of something beautiful and eternal? Or do they embrace it, recognizing that all things are temporary, that even the most permanent-seeming features of the cosmos are subject to change? There's another possibility. Maybe an advanced civilization decides to save the rings. With sufficiently advanced technology, you could replenish the ring system, launch material from Earth, or capture asteroids and put them into orbit at the right altitude. It would be an enormous undertaking, requiring vast amounts of energy and resources, but it's not physically impossible. Or maybe a civilization decides to accelerate the decay, deliberately clearing the rings to make space travel safer. They could use lasers or mass drivers to push ring particles out of orbit, causing them to burn up in the atmosphere more quickly. Within a few centuries, the rings could be gone, and humanity would see a clear sky for the first time in its history. The stars would shine unobstructed. The Milky Way would be visible in all its glory. It would be like opening a window after living in a closed room your entire life. Some people would celebrate this new view. Others would feel a profound sense of loss, a nostalgia for the ringed skies of their ancestors. Either way, it would mark a turning point in human history, the moment when we transitioned from a species living under rings to a species living under open sky. The psychological and cultural impact would be immense, comparable to any other great transition in human development. The rings, in their presence and in their absence, would shape us. They would make us who we are. And when they finally vanished, whether through natural decay or deliberate action, we would carry their memory forward, a reminder of the world that was and the world that might have been. You wake up one morning in a world with rings. You stumble out of bed, make coffee, and look out the window. There they are, as they've always been. A luminous arc stretching across the dawn sky, glowing pink and gold as the first rays of sunlight catch the ice particles orbiting thousands of kilometers above. You don't think much about it. Why would you? The rings have been there your entire life, just like the ground beneath your feet and the air in your lungs. But, as you go about your day, those rings are quietly influencing everything. The weather, the technology you use, the economy, the very structure of modern civilization. Let's start with something immediate and tangible: the climate. We've already discussed how the rings cast shadows on Earth's surface, creating bands of reduced sunlight in equatorial regions. But what does this actually do to the weather? Sunlight drives climate. It warms the surface, evaporates water, creates air currents. When you reduce the amount of sunlight hitting a particular region, you cool it down. The equatorial ring shadow would create a zone that's several degrees cooler than it would be in a world without rings. Several degrees might not sound like much, but it's enough to shift weather patterns. The tropics, which in our world are characterized by intense heat and heavy rainfall, would be slightly more temperate under the rings. Rainforests might be less dense. Deserts might be less extreme. The seasonal shift of the ring shadow would create a migration of climate zones. During the northern summer, when the ring shadow is concentrated in the southern hemisphere, the Amazon basin would experience cooler temperatures and altered rainfall patterns. 6 months later, the shadow shifts north, and regions like Central Africa and Southeast Asia get their turn under reduced sunlight. This would affect agriculture profoundly. Farmers would have to adapt to the ring shadow seasons. Crops that thrive in full sunlight would be planted during the bright season, when the shadow has moved away. Crops that prefer cooler temperatures would be planted when the shadow is overhead. Agricultural calendars would be more complex, but also more predictable, because the ring shadow is far more regular than weather in our timeline. You always know exactly when the shadow season is coming. There's no year-to-year variation. This predictability would make farming more reliable in some ways, reducing the risk of unexpected crop failures. But it would also create new vulnerabilities. If a crop is perfectly adapted to the bright season and the shadow season, it might not be adaptable to climate changes caused by other factors, like volcanic eruptions or long-term climate shifts. The ring shadow would also influence ocean currents. Surface water temperature drives currents like the Gulf Stream and the Kuroshio Current, which transport heat around the planet and moderate coastal climates. With the equatorial regions being slightly cooler due to the ring shadow, these currents would be weaker or shifted in latitude. Coastal regions in Europe and North America that benefit from the Gulf Stream's warmth would be colder. Winters would be harsher. Growing seasons would be shorter. Entire civilizations might develop in different locations, chasing the optimal climate zones that exist in a ringed world, but not in ours. And then there's the psychological effect of the ring shadow. Imagine living near the equator, where every single day includes a few hours of twilight caused by the rings blocking the sun. You're not in darkness, but the light is dim, diffused, eerie. Colors look different. Shadows are softer. If you've ever experienced a solar eclipse, you know that strange quality the light takes on, how everything seems muted and otherworldly. Now, imagine that happening every single day. Some people would love it. Those few hours of ring shadow would be the best part of the day, a respite from the tropical heat, a time when it's cool enough to work outside without sweating through your clothes. But others would find it oppressive. Seasonal affective disorder, which in our world is triggered by reduced sunlight during winter, might be triggered by the daily ring shadow in a ringed world. People living in equatorial regions might experience depression, lethargy, and mood disorders linked to the shadow hours. Cultures would develop coping mechanisms. Maybe the shadow hours are designated for rest and indoor activities, while the bright hours are for work. Maybe artificial lighting becomes extremely important, even in pre-industrial societies. Oil lamps, candles, torches, anything to push back the gloom during the shadow hours. Now, let's talk about the night sky and light pollution. In our world, artificial light from cities has largely ruined the view of the stars. Most people living in urban areas can't see the Milky Way. They're lucky if they can see a few dozen stars. But in a ringed world, the rings themselves would be a source of light pollution, except it's natural. When the rings are fully illuminated at night, they'd be bright enough to wash out all but the brightest stars. The sky would never be truly dark. You'd see the rings, the moon if it's up, and maybe a handful of planets and the very brightest stars like Sirius and Vega. But the thousands of stars visible from a dark site in our world would be invisible. The Milky Way would be partially or completely obscured. Astronomers would face a unique challenge. To see faint objects like distant galaxies or nebulae, they'd need to observe during the new moon and during the brief periods when the rings are in Earth's shadow. Those few hours each night when the rings are dark would be precious. Observatories would be scheduled around the ring shadow the same way modern observatories schedule around the lunar cycle. There'd be intense competition for observation time during the optimal hours. Alternatively, astronomers might build observatories at the poles, where the rings hug the horizon and obstruct less of the sky. Antarctica and the Arctic would become centers of astronomical research much earlier in history. On the other hand, the rings themselves would be spectacular objects for observation. With even a small telescope, you'd be able to see structure in the rings, gaps, density variations, shepherd moons. Amateur astronomers would spend their evenings sketching the rings, noting changes, discovering new features. The rings would be to astronomy in a ringed world what the moon is to astronomy in ours, the most accessible and most studied celestial object. Professional astronomers would use large telescopes to study the composition of ring particles, through spectroscopy, to track the orbits of shepherd moons with extraordinary precision, to search for embedded moonlets that are too small to see from the ground. The rings would be a laboratory for orbital mechanics and collisional dynamics right in our backyard. But here's where things get difficult. Let's talk about satellites. In our world, we rely on satellites for communication, navigation, weather forecasting, Earth observation, scientific research, and more. Thousands of satellites orbit Earth, and they've become essential to modern civilization. In a ringed world, satellites would be a nightmare. The rings occupy a band of space from about 7,000 kilometers altitude out to perhaps 80,000 kilometers. That's prime real estate for satellites. Geostationary orbit, where satellites orbit at the same rate Earth rotates and thus appear fixed in the sky, sits at 35,786 kilometers. That's right in the middle of the ring system. You can't put a satellite there without it constantly colliding with ring particles. Even outside the main ring system, the space around Earth would be littered with stray particles and debris. Launching a satellite would be like navigating a minefield. You'd need to find gaps in the rings, which means your satellite can only orbit at certain altitudes, and even then, you'd have to deal with the risk of collisions. Low Earth orbit, below the rings, would be relatively safe. This is where the International Space Station orbits in our timeline, at an altitude of about 400 kilometers. Satellites in this zone would be below the rings, but they'd still be vulnerable to ring particles that are spiraling inward and burning up in the atmosphere. You'd need robust shielding and frequent maintenance missions to repair or replace damaged satellites. The lifetime of a satellite would be much shorter. What lasts 10 years in our world might last only 2 or 3 years in a ringed world. The cost of maintaining a satellite network would be enormous. GPS, or whatever navigation system exists in a ringed world, would be much more expensive and much less reliable. Instead of a constellation of 30 satellites providing global coverage, you might need 100 satellites, constantly being replaced as they're damaged or destroyed. Communication satellites would face similar problems. In our world, geostationary satellites are perfect for communication because they stay fixed over one point on the equator, allowing ground stations to point their antennas at a single location. In a ringed world, geostationary orbit is unusable. You'd have to rely on low Earth orbit satellites, which move across the sky and require tracking antennas. Or you'd use polar orbits, satellites that pass over the North and South poles and avoid the equatorial ring plane. Polar satellites are useful, but they don't provide the same continuous coverage as geostationary satellites. There would be gaps in coverage. Times when no satellite is overhead and communication is impossible. Global internet, if it exists, would be intermittent and expensive. Video calls might be a luxury reserved for the wealthy or for critical business. Most people would rely on older technologies like telephone landlines or radio. Weather satellites, which in our world sit in geostationary orbit and provide continuous monitoring of weather systems, would be forced into low Earth orbit or polar orbits. Weather forecasting would be less accurate. Hurricanes might not be spotted until they're much closer to land. Tornado warnings would be less reliable. Agriculture, shipping, aviation, all industries that depend on accurate weather forecasts would face greater uncertainty and risk. The economic impact would be substantial. On the other hand, some technologies might develop faster in a ringed world. If satellites are difficult and expensive, ground-based alternatives would be more attractive. Maybe fiber optic cables connecting continents become the primary means of long-distance communication, with undersea cables crisscrossing the oceans decades or even centuries earlier than in our timeline. Maybe ground-based radar and weather stations become more sophisticated. compensating for the lack of satellites with denser networks of sensors. Maybe communication towers are built taller, with more powerful transmitters to extend the range of radio signals. And what about space exploration? Getting to space in a ringed world would be orders of magnitude more dangerous. Every rocket launch would have to navigate through or around the rings. The safest approach would be to launch from high latitudes and use a polar trajectory, passing over the poles where the ring density is lowest. This means the ideal locations for spaceports would be places like Alaska, Norway, Siberia, Patagonia, or New Zealand. Equatorial launch sites, which in our world are preferred because Earth's rotation gives rockets a speed boost, would be nearly useless. You'd be launching directly into the densest part of the ring system. Even with polar launches, there's risk. Ring particles extend above and below the main ring plane, especially near the edges of gaps or in regions where shepherd moons have stirred things up. A rocket during ascent is moving at several kilometers per second. If it hits even a small ring particle, the result would be catastrophic. Imagine a pebble-sized chunk of ice hitting a rocket at orbital velocity. It would punch through the hull like a bullet through paper. The rocket would explode. The crew, if any, would die instantly. To mitigate this risk, rockets would need heavy shielding, especially around critical components like fuel tanks and crew modules. But shielding adds mass, which reduces payload capacity. A rocket that can carry 10 tons to orbit in our world might only carry 5 tons in a ringed world because half the payload capacity is eaten up by shielding. This makes space access more expensive and less efficient. It also slows down the development of space technology. The space race, if it happens at all, would be slower and more cautious. The Apollo program might take 20 years instead of 10. The International Space Station might not exist, or it might be much smaller, because launching and assembling modules is so difficult. Or maybe space programs focus on different goals. Instead of satellites and space stations, maybe the focus is on ground-based infrastructure. Or maybe space programs are abandoned entirely, deemed too risky and too expensive. Humanity remains earthbound, looking up at the rings with longing and frustration, knowing that the beautiful arc in the sky is also a barrier trapping us on the surface. But let's assume space programs do develop, slowly and cautiously. What would space travel look like? Astronauts would need to time their launches carefully, threading through gaps in the rings during brief windows when the trajectory is clear. Mission planning would be incredibly complex. You'd need real-time tracking of ring particles, predictive models of their orbits, contingency plans for debris strikes. Every mission would be a high-stakes gamble. And if a mission failed, if a rocket was destroyed by a ring collision, public support for space exploration would plummet. The death of astronauts in our timeline, like the Challenger and Columbia disasters, led to years of soul-searching and program delays. In a ringed world, such disasters would be more frequent, and the political will to continue might not exist. Assuming astronauts do make it to space, what would they see? The view of the rings from orbit would be breathtaking. Instead of looking up at the rings from the ground, you'd be among them, flying through gaps, seeing the ring particles up close, watching sunlight glint off billions of ice crystals. The rings would no longer be a distant arc, but a three-dimensional structure surrounding you. Astronauts would describe it as flying through a snowstorm that never ends, except the snowflakes are frozen in place, each one orbiting at its own speed. Photographs taken from space would be unlike anything in our timeline. The rings stretching across the void, Earth visible through gaps, the moon rising above the ring plane. These images would inspire awe and wonder, reminding people why we venture into space despite the risks. And what about the moon? In our world, the moon is Earth's only natural satellite, orbiting at a safe distance. In a ringed world, the moon would still be there, orbiting far beyond the rings. But its presence would complicate the ring system. The moon's gravity would perturb the orbits of ring particles, especially those in the outer regions. Some particles might be pulled out of the ring plane, creating a diffuse halo of debris around the main rings. Others might be flung outward, either escaping Earth entirely or settling into stable orbits between the outside rings and the moon. The moon itself would occasionally pass through the ring plane, plowing through any stray particles in its path. These encounters would be brief and mostly harmless to the moon, but they'd create spectacular meteor showers as displaced ring particles burn up in Earth's atmosphere. Ancient peoples would interpret these showers as omens, signs that the moon and the rings are communicating or battling. Now, let's talk about aviation. In our world, airplanes fly at altitudes between 10 and 15 kilometers, well below the altitude of satellites but high enough to avoid most weather. In a ringed world, airplanes would still fly at similar altitudes below the rings. But the constant rain of meteorites from the rings would create new hazards. Most meteorites burn up at altitudes above 50 kilometers, but some survive longer, and there's a small but non-zero chance that a meteorite could hit an airplane in flight. It would be extraordinarily rare, but with thousands of flights per day, rare events eventually happen. Airlines would need to account for this risk. Maybe flight paths are designed to avoid the equatorial regions where ringfall is most intense. Maybe planes have reinforced fuselages to withstand small impacts. Maybe there's a meteorite warning system, tracking incoming debris and rerouting flights if necessary. The cost and complexity of air travel would increase, but probably not enough to make it impractical. Flying would just be slightly more dangerous and slightly more expensive. Another issue is visibility. Pilots rely on seeing the horizon, landmarks, and other aircraft. The rings, especially during the day when they're brightly lit, would dominate the sky. In some lighting conditions, the rings might create glare or make it harder to spot other planes. Pilots would need training to navigate under ringed skies, learning to mentally filter out the rings and focus on what's important. Night flights would be easier in some ways because the illuminated rings would provide ambient light, making it easier to see the ground. But they'd also make it harder to see stars, which pilots sometimes use for navigation. Then there's the economic impact. Tourism would be completely different in a ringed world. In our timeline, people travel to see natural wonders like the Grand Canyon, the Northern Lights, or a total solar eclipse. In a ringed world, the rings themselves would be the ultimate tourist attraction. Except you don't have to travel to see them. They're visible from anywhere on Earth, weather permitting. So what would drive tourism? Probably the quest to see the rings from different perspectives. Equatorial resorts would advertise the experience of standing directly beneath the rings, seeing them as a thin line overhead. Mid-latitude destinations would offer the best view of the ring arc, the dramatic sweep across the sky. Polar expeditions would promise the sight of the rings forming a complete circle around the eye horizon, and high-altitude locations, mountains and plateaus, would offer clearer views above the haze and pollution of lower elevations. There might also be dark sky tourism, trips to locations and times when the rings are in Earth's shadow and the stars are visible. Astronomy enthusiasts would plan vacations around the new moon and the ring shadow, traveling to remote locations to see the Milky Way unobstructed for a few precious hours. These dark sky events would be as highly anticipated as solar eclipses in our world. Hotels and tour operators would book up months in advance. Local economies would boom during these brief windows of darkness. And then there's real estate. Property values would be influenced by ring visibility. Homes with a clear view of the rings would sell for a premium. Architects would design buildings to frame the rings, with large windows or open courtyards offering unobstructed sightlines. In equatorial regions where the rings appear as a thin line, some people might prefer homes oriented east-west to maximize the view. In mid-latitudes, south-facing homes in the northern hemisphere and north-facing homes in the southern hemisphere would be most desirable, offering the best view of the ring arc. Culturally, the rings would permeate every aspect of modern life. Advertising would use ring imagery constantly. Romantic movies would feature scenes of couples watching the rings at sunset. Children's books would anthropomorphize the rings, giving them personalities and voices. National flags might incorporate ring motifs, stylized arcs or circles representing the rings. Sports teams would name themselves after ring-related concepts. The Houston Arcs, the Singapore Shadows, the Oslo Ring Chasers. The rings would be as embedded in popular culture as the Eiffel Tower or the Statue of Liberty or Mount Fuji, except they'd be visible everywhere, all the time, making them even more iconic. And finally, there's the question of how people feel about the rings on a personal level. In our world, people have different relationships with the moon. Some find it beautiful and romantic. Others barely notice it. A few are obsessed with it, planning their lives around lunar phases. In a ringed world, the relationship would be even more complex. The rings are bigger, brighter, and more constant than the moon. You can't ignore them. They're always there, shaping the light, casting shadows, filling the sky. Some people would love them, finding comfort and beauty in their presence. Others would resent them, feeling oppressed by the constant reminder of something beyond human control. And a few would be indifferent, so accustomed to the rings that they barely register them consciously. But everyone would be shaped by them. Growing up under ringed skies would create a fundamentally different psychology, a different sense of scale and place. You'd know, viscerally, that you live on a planet, that the ground beneath your feet is a sphere surrounded by orbiting debris, that the universe is not distant and abstract but immediate and present. Whether that knowledge would make people more humble or more ambitious, more connected to the cosmos or more focused on earthly concerns, is impossible to say. But it would change us. The rings would make us different from who we are now, in ways both subtle and profound, shaping human consciousness just as much as they shape the sky above. So far, we've explored what life would be like on the surface of a ringed Earth. But now it's time to ask the most ambitious question of all. What would it take to actually get to space? How would humanity's journey beyond Earth change if we had to navigate through billions of orbiting particles just to reach the stars? And, perhaps most intriguingly, what would we find if we sent astronauts to explore the rings themselves? The answer is that spaceflight would be fundamentally transformed, more dangerous and more expensive, but also potentially more rewarding. Because while the rings would create unprecedented obstacles, they might also provide unprecedented opportunities. Let's start with the basic problem. launch windows. In our world, rockets can launch from any location at almost any time, with the main constraints being weather and orbital mechanics. If you want to reach the International Space Station, you need to launch when Earth's rotation carries your launch site into the plane of the station's orbit. If you want to go to the Moon, you need to time your launch to meet the Moon at the right point in its orbit. These constraints create launch windows, specific times when a mission is possible, but those windows come around frequently. Daily for some missions, weekly for others. In a ringed world, launch windows would be measured in months or even years. Here's why. The rings occupy a thick band of space around Earth's equator. Any rocket launching from mid or low latitudes would have to pass through this band. But the rings aren't uniformly distributed. There are gaps, regions where the ring density is lower due to the gravitational influence of shepherd moons or orbital resonances. These gaps are like corridors through the rings, relatively clear paths where a rocket has a reasonable chance of making it through without getting hit. The problem is that these gaps are narrow and they're moving. The ring particles at different distances orbit at different speeds, so the gaps shift position over time. A gap that's aligned with your launch trajectory today might be completely blocked tomorrow. Mission planners would need to calculate not just where the gaps are now, but where they'll be at the moment your rocket passes through that altitude. This requires extraordinarily precise orbital mechanics and timing. You'd also need to account for the fact that your rocket is accelerating. It's not moving at constant speed. It starts slow and speeds up as it climbs. This means it spends different amounts of time at different altitudes, and the gaps are moving relative to your position. The math becomes fiendishly complex. The safest strategy would be to avoid the problem entirely by launching from high latitudes and going polar. If you launch from northern Alaska or northern Norway or Siberia and angle your trajectory over the North Pole, you pass over the top of the rings where they're nearly edge-on and the particle density is lowest. The same applies to launches from southern Argentina, southern Chile, or Antarctica heading over the South Pole. This is why spaceports in a ringed world would cluster near the poles rather than the equator. But polar launches have their own disadvantages. In our world, launching from near the equator is ideal because Earth's rotation gives you a velocity boost. At the equator, the surface of Earth is moving eastward at about 465 meters per second due to rotation. If you launch eastward, you get that speed for free, reducing the amount of fuel needed to reach orbit. At the poles, Earth's rotational velocity is zero. You get no boost. Every meter per second of velocity has to come from your rocket engines, which means you need more fuel, which means a heavier rocket, which means more expense. A rocket that could carry 10 tons to orbit from an equatorial launch site might only carry 7 or 8 tons from a polar site. That's a significant penalty, but there's no choice. Equatorial launches in a ringed world would be suicide. Even if you could find a gap in the rings, the risk would be too high. A single miscalculation, a single unexpected collision between ring particles that closes your gap at the wrong moment, and your rocket is destroyed. No space agency would accept those odds, especially for crewed missions. So, polar launches become the standard, despite the efficiency penalty. This changes the geography of space exploration. In our timeline, major spaceports are located in places like Florida, French Guiana, Kazakhstan, and China, all relatively low-latitude sites chosen for their proximity to the equator. In a ringed timeline, the major spaceports would be in Alaska, Scandinavia, Russia's far north, Patagonia, and Antarctica. These are remote, harsh environments with extreme weather. Launching rockets in sub-zero temperatures with high winds and frequent storms would add another layer of difficulty. The cost and complexity of space access would skyrocket, pun very much intended. Assuming you do manage to launch successfully and thread your way past the rings, what comes next? In our world, once you're in orbit, space is relatively empty. You can maneuver freely, and the main concerns are fuel and life support. In a ringed world, even after you've cleared the main ring system, you're still in a debris field. Stray particles that have been knocked out of the ring plane by collisions or gravitational perturbations are scattered throughout near-Earth space. Any spacecraft would need heavy shielding, not just during launch, but for the entire mission. The International Space Station in our timeline has shielding to protect against micrometeorites and orbital debris, but it's relatively light because collisions are rare. In a ringed world, collisions would be orders of magnitude more common. The ISS equivalent might need armor plating several centimeters thick, adding massive amounts of weight and cost. Spacecraft design would prioritize survivability over efficiency. Fuel tanks and crew modules would be buried deep inside the structure, surrounded by layers of protective material. Solar panels, which are fragile and exposed, would be a major vulnerability. A single ring particle punching through a solar panel could cripple a spacecraft's power supply. Engineers might abandon solar panels entirely in favor of nuclear reactors or radioisotope thermoelectric generators, despite the added complexity and political sensitivity. Every design decision would be a trade-off between protection and practicality. The result would be spacecraft that are bulkier, heavier, and more expensive than anything we've built in our timeline. Space stations might not exist at all, or they'd be much smaller and located in carefully chosen orbits that minimize exposure to ring debris. Crewed missions beyond low Earth orbit to the Moon or Mars would be even more daunting because the spacecraft would need to carry all that shielding for the entire journey. But let's imagine that despite all these obstacles, a space program does develop. Rockets are launched from polar sites. Spacecraft are heavily armored. Astronauts accept the risks. What would be the first priority for such a program? In our timeline, early space missions focused on reaching orbit, then the Moon, then establishing a presence in low Earth orbit with space stations. In a ringed timeline, the first priority might be different. It might be the rings themselves. Because the rings aren't just an obstacle, they're also a resource. Think about what the rings are made of. If they formed from a disrupted icy moon, they're primarily water ice with some rocky material mixed in. Water is incredibly valuable in space. You can drink it, obviously, but you can also split it into hydrogen and oxygen. Hydrogen and oxygen are rocket fuel. They're also breathable air for life support. A spacecraft that can refuel from the rings doesn't need to carry all its fuel from Earth. It can launch with a minimal fuel load, rendezvous with the rings, harvest ice, process it into fuel, and then continue on to its destination. This would revolutionize spaceflight, making missions cheaper and more flexible. The rings would also provide raw materials for construction. Ice can be used as radiation shielding. It's effective at blocking cosmic rays and solar radiation, and it's much cheaper than launching metal shielding from Earth. You could build spacecraft or space stations in orbit, using ice harvested from the rings as structural, material, and shielding. Rocky material in the rings could be processed for metals and minerals. If the rings contain iron, aluminum, or titanium, those could be extracted and used for manufacturing. The rings would become a quarry, a source of materials for an entire orbital economy. But to exploit the rings, you'd first need to reach them, and that means sending astronauts or robotic probes into the ring system, which is extremely dangerous. The ring particles are orbiting at several kilometers per second. If your spacecraft is also in orbit, you're moving at roughly the same speed as the particles around you, so relative velocities are low. You could, in theory, approach a large ring particle slowly and carefully, matching its orbit, and then land on it or grapple it with a robotic arm. This is how asteroid mining is envisioned in our timeline, and the same principles would apply to ring mining. But there are complications. The rings are densely packed compared to the asteroid belt. In the asteroid belt, objects are separated by millions of kilometers. In the rings, particles are separated by meters or kilometers. This means your spacecraft is constantly at risk of collision, not just with the particle you're targeting, but with others nearby. Navigation would require real-time tracking of thousands of particles, predictive algorithms to avoid collisions, and a lot of luck. Any mistake would be fatal. A spacecraft clipping a ring particle at orbital velocity would be shredded instantly. Despite the risks, the potential rewards are enormous. A single mission that successfully retrieves a few tons of ice from the rings could pay for itself many times over by providing fuel for other missions. A permanent mining operation, with spacecraft constantly shuttling between the rings and a processing facility in a safer orbit, could supply the entire space program with fuel and materials at a fraction of the cost of launching from Earth. This would make ambitious projects like lunar bases or Mars missions economically feasible. The rings, for all the problems they cause, might also be the key to unlocking the solar system. Now, let's imagine what it would actually be like to visit the rings as an astronaut. You launch from a polar spaceport, endure the weeks or months of travel to reach the ring system, and finally arrive. What do you see? From a distance, the rings look much as they do from the ground, a bright band stretching across space. But as you get closer, the band resolves into individual particles. At first, they're just points of light, glints of sunlight reflecting off ice. But as you approach, the points become chunks, boulders, some as small as pebbles, others as large as houses. They're tumbling slowly, their irregular shapes catching the light in flashes and glimmers. The space around you is filled with them, a three-dimensional blizzard frozen in time. Except it's not frozen. The particles are moving, orbiting Earth, and you're moving with them. The effect is disorienting. You feel like you're stationary, but the planet below is rotating. The stars are wheeling overhead, and the particles around you are drifting in complex patterns dictated by gravity and momentum. You maneuver carefully, using small thruster bursts to edge closer to a large chunk of ice. It's maybe 10 meters across, irregular, pockmarked with craters from countless collisions with smaller particles. The surface is dirty, a mix of white ice and dark rocky dust. You extend a robotic arm, grab the chunk, and pull it toward your spacecraft. As it gets closer, you see details, fractures running through the ice, evidence of internal stress. Small particles embedded in the surface, frozen in place. This chunk is ancient, a fragment of the moon that was destroyed to create the rings, and it's been orbiting Earth for millions of years, slowly eroding, slowly shrinking. You secure it to your spacecraft and begin the journey back. The ice will be processed, melted, purified, and electrolyzed into hydrogen and oxygen. Some will be used as fuel, some will be stored for life support, and some will be studied, analyzed for clues about the rings' formation and composition. Every mission to the rings brings back not just resources, but knowledge. Over time, a picture would emerge. Scientists would learn the exact composition of the rings, the ratio of ice to rock, the distribution of particle sizes. They'd discover anomalies, regions where the composition is different, hinting at multiple sources of material or complex formation processes. They'd find shepherd moons, small bodies shepherding the rings and maintaining gaps, and study their geology and orbits. Some of these moons might be large enough to land on, offering stable platforms for scientific outposts or mining operations. A crewed mission to a shepherd moon would be one of the great achievements of space exploration in a ringed timeline, comparable to landing on the moon in hours. Astronauts would plant a flag on the surface of a tiny world, with the rings stretching out in every direction, a glowing band encircling the sky. Earth would be visible beyond the rings, a blue and white sphere slowly rotating. The photos from such a mission would be iconic, defining images of human achievement and exploration. But let's not forget the dangers. Space is already the most hostile environment humans have ever ventured into. Vacuum, radiation, extreme temperatures, isolation. The rings add another layer of hazard. A spacecraft in the ring system is under constant threat of collision. Redundancy becomes essential. Multiple layers of shielding. Backup systems for critical functions. Abort procedures for every phase of the mission. Despite all precautions, accidents would happen. A spacecraft might be struck by a particle that wasn't detected in time. The crew might survive if the impact doesn't breach the pressure hull, but the mission would be aborted, and they'd limp back to safety. Or they might not survive. The history of space exploration in a ringed timeline would be written in the names of astronauts who died in the rings, remembered as pioneers who gave their lives to push the boundaries of human knowledge. Their sacrifices would be honored, but the question would always linger: is it worth it? Are the resources and knowledge gained from the rings worth the cost in lives and treasure? Different societies would answer that question differently. Some might embrace the challenge, pouring resources into ring exploration and exploitation, seeing it as humanity's destiny to master the space around Earth before venturing farther. Others might reject it, arguing that the rings are too dangerous, that we should focus on robotic missions or ground-based science, that risking human lives for ice and rock is folly. The debate would echo the debates we have in our timeline about the value and purpose of space exploration, but with higher stakes and more tangible dangers. Public opinion would swing based on successes and failures. A successful ring mining operation that produces cheap fuel for a Mars mission would boost support. A disaster that kills a crew would erode it. The political and cultural landscape of space exploration would be shaped by the rings in ways both predictable and surprising. And what about the long-term future? Assuming humanity survives and thrives, what role would the rings play in a spacefaring civilization centuries or millennia from now? One possibility is that the rings are eventually cleared, deliberately or naturally. As we discussed in Part 3, the rings are slowly decaying, raining down on Earth over millions of years. An advanced civilization might accelerate this process, using technology to push ring particles out of stable orbits and clear the space around Earth. This would make space access safer and easier, opening up geostationary orbit and other valuable regions for satellites and infrastructure. But it would also mean the end of the rings, the loss of the feature that has defined Earth's sky for as long as humans have existed. The decision to clear the rings would be monumental, debated for generations. Some would argue it's necessary for progress, that humanity can't be held back by sentimental attachment to a natural phenomenon. Others would fight to preserve the rings, seeing them as a priceless part of Earth's heritage, irreplaceable and sacred. Environmental movements might form around ring preservation, arguing that the rings are the part of Earth's ecosystem, that their shadows influence climate and weather in ways we don't fully understand, that destroying them would be an ecological catastrophe. Another possibility is that the rings are maintained and enhanced. Instead of clearing them, we add to them, launching material from Earth or redirecting asteroids to replenish the ring system. The rings become a permanent feature, carefully managed and shaped to serve human needs. Gaps could be widened to create safe corridors for spacecraft. Dense regions could be mined out, leaving behind a skeleton of the original ring. Shepherd moons could be adjusted or replaced with artificial satellites that maintain the ring structure. The rings would transition from a natural phenomenon to an engineered system, a megastructure encircling Earth. This might sound like science fiction, and it is, but it's not physically impossible. With sufficient technology and motivation, it could be done. The rings would become a monument to human ambition, a testament to our ability to reshape the cosmos. Or they might be seen as a hubristic folly, an example of humanity's arrogance in thinking we can improve on nature. There's also the possibility that the rings become a home, not just a resource to be exploited, but a place to live. Habitats could be built within the ring system, rotating structures that provide artificial gravity for their inhabitants. These habitats would orbit Earth just like the ring particles, but they'd be large and sophisticated, supporting populations of thousands or even millions. The rings would transition from an obstacle to an environment, a new frontier for human settlement. People born and raised in ring habitats would grow up surrounded by ice and rock, with Earth always visible below and the stars unobstructed above. They'd have a perspective unlike anyone on the surface, living in space but still tethered to Earth, part of the planet's system but not bound to its surface. Their culture and identity would be shaped by this unique position, and they might come to see themselves as distinct from Earthbound humans, the beginning of a divergence that could eventually lead to separate branches of humanity. But all of this is speculation, distant possibilities that depend on countless variables. What we can say with more certainty is that the rings would shape the trajectory of human spaceflight in profound ways. They'd make space access harder, forcing us to innovate, to develop new technologies and strategies. They'd provide resources that could enable missions otherwise beyond our reach. They'd inspire us with their beauty and challenge us with their danger. Every rocket that launched from a polar spaceport, every astronaut who ventured into the ring system, every scientist who studied the particles and moons would be part of a grand endeavor shaped by the presence of those glowing arcs in the sky. And through it all, the rings would remain, orbiting silently, indifferent to human struggles and triumphs, a reminder that we live in a cosmos far larger and stranger than ourselves. So, what's the final answer? Would Earth be better or worse with rings? It's impossible to say, because better and worse are subjective. A world with rings would be different, not just in superficial ways but fundamentally. The climate would be different, the night sky would be different. Human culture, religion, science, and technology would all develop along different paths. We'd face challenges that don't exist in our timeline, and we'd have opportunities that don't exist either. Some people would thrive in a ringed world, finding meaning and beauty in the arcs overhead. Others would struggle, oppressed by the shadows, the meteorites, the barriers to space. But that's true of any world, including the one we actually inhabit. Every environment shapes the life within it, creating both constraints and possibilities. The question isn't whether we'd prefer a ringed Earth, because we can't choose. We're shaped by the world we're born into, and we make the best of it. The question is what we can learn from imagining a different world. And what we learn is this: the features of our planet that we take for granted, the clear sky, the stable climate, the ease of space access, these aren't inevitable. They're contingent on countless factors, accidents of formation and evolution that could have gone differently. Earth could have had rings. It might have had them in the past. It might have them in the future if a moon is destroyed or an asteroid is captured. And if that happened, we'd adapt, just as we've adapted to every other challenge in our history. We'd look up at the rings and tell stories about them. We'd build our lives around them. We'd find ways to navigate through them and eventually to explore them. Because that's what humans do. We're shaped by our environment, but we also shape it in return. We're not passive recipients of whatever the cosmos throws at us. We're active participants, struggling and striving to understand and ultimately to transcend the circumstances of our existence. The rings, in the end, are a metaphor. They represent the obstacles we face, the beauty we find, and the ingenuity we bring to bear when confronted with the unknown. Whether those obstacles are literal rings of ice and rock orbiting our planet, or metaphorical barriers of distance, ignorance, and limitation, the challenge is the same. We look up, we wonder, we question, and eventually we reach. We extend our hands and our minds beyond the immediate and familiar, seeking something greater. Sometimes we fail. Sometimes the cost is too high, the risks too great. But sometimes we succeed, and those moments of success, those breakthroughs and discoveries, those times when we push past what we thought was possible, those are the moments that define us. A ringed Earth would give us more opportunities for both failure and success. It would test us in new ways and reward us with new wonders, and in the process, it would make us different, not better or worse, but undeniably and irreversibly changed. So when you look up at the clear, ring-free sky of our actual Earth, maybe take a moment to appreciate it. And then imagine, just for a moment, what could have been. A glowing arc stretching from horizon to horizon, bright enough to cast shadows, beautiful enough to inspire awe, and complex enough to occupy human minds for thousands of years. That's the world we've explored together. A world that never was, but could have been. A world with rings.